Hi, today I would like to present our work on prior guided source-free domain adaptation for human pose estimation. The task of 2D pose estimation is fairly straightforward. Given the image of a person, we want to be able to estimate the spatial locations of predefined key points within the image. This has several important applications such as action recognition, 3D pose and body shape estimation, and biometrics. Current methods for pose estimation use convolutional neural networks in order to extract features and predict the key points in an image. However, because of this, these methods also suffer from poor performance due to domain shifts, which is a well-known problem with CNNs. For example, a pose estimation model trained on synthetic data does not perform as well on real-world data. In order to address this domain shift, there has been a large amount of research in the problem of unsupervised domain adaptation, where we have an annotated source dataset, an unlabeled target dataset, and some joint training strategy. However, while these methods work fairly well, there is an issue in which they require the source data during adaptation, which there are some practical issues such as privacy and memory constraints. With privacy concerns growing by the day, it is important to be able to adapt a model without relying on a source dataset that may be taken offline, or a dataset where a subject has revoked their consent to be used for training. The goal of our work is to be able to adapt a pre-trained pose estimation model using only the unlabeled target data, and as we find out, it works almost just as well. To give it an overview of our approach, we first start with the mean teacher setup, in which the teacher and student model both take in different augmented views of the same image, and then we enforce a consistency in the prediction or output space of both models in order to then update the student model parameters with respect to that loss. And then the teacher model is updated as an exponential moving average of the weights of the student model. In addition to enforcing consistency on the output space, we also enforce an additional consistency in the feature space between the student and teacher model using the Barlow-Twins approach, in which we want to minimize the difference between the estimated cross-correlation matrix between the student and teacher features and the identity matrix. Finally, we add a pose prior to our model in order to regularize our model into predicting more plausible poses. Inspired by recent work on using implicit neural representations for 3D pose modeling, we also choose to model the manifold of plausible 2D poses as a level set where the distance of real poses is 0. We then add von Mises noise to the real poses in order to generate noisy poses. The distance of these noisy poses is then assigned by sampling k nearest neighbors of real poses and computing the average distance. This prior is then trained as an end-to-end regression model to estimate the distance a pose lies from the manifold. For our experimental setup, we train our model on the surreal dataset and then test the cross-domain performance on 2 different datasets. Specifically, we test on the LSP and Humans 3.6M dataset. Our results show that without the source dataset, we are still able to beat many existing unsupervised domain adaptation methods and get close to the state-of-the-art for unsupervised domain adaptation without the source data. Additionally, we see that on the bottom plot that our prior is able to accurately predict what are plausible poses from noisy poses across datasets. In addition to the quantitative results that we showed on LSP and Humans 3.6M, we also have qualitative results on the Breyer dataset. The Breyer dataset consists of people in outdoor scenarios at varying distances and includes a large number of potential factors that can affect the image quality, such as atmospheric turbulence or motion blur. Our model, however, is still able to adapt fairly well to this dataset and even handle cases where there is wildly differing camera perspectives from the source dataset, such as higher elevation from a UAV-mounted camera. And that concludes this presentation. Thank you.